Welcome to the second tutorial covering the use of Curvy version 2.0. In this video, we will be covering the meat of the package, splines themselves. As we have seen in the introduction video, every spline requires a spline object, that is a game object with a Curvy spline component attached, and a set of control points, that is game objects with Curvy spline segment component attached. Control point objects are parented to a spline object. Now, how are those isolated control points creating a continuous path? Well, this is pretty simple. This component is not only responsible for a control point itself. When you select it, notice how part of a spline after it is highlighted too. That part, spanning from a currently selected control point to a next control point, is called a segment, and every control point is responsible for one. That's why the control point component is called Curvy Spline Segment in the first place. Despite being governed by some complex mass, splines work on a pretty simple principle. You define them with control points, and then you feed them so-called time or fragment value, a number from 0 to 1. Code in Curvy frequently refers to this value with just one letter, f, for fragment. A spline then returns a position for that given f value. If you are familiar with linear interpolation between two positions, this will be an easy concept for you to grasp. An f value of 0 will give you a position in the beginning of a segment, and an f value of 1 will give you a position in the end of a segment. There are two types of fragment values: local fragment value, referring to a point within a segment, and total fragment value, referring to a point in the whole spline. If you want a point, for example, midway between control points 2 and 3, you ask for local f value of 0.5 from control point 2. If instead you want a position at the midpoint of a spline, you ask for total f value of 0.5 from the spline object. Note though that total f distribution on the spline has absolutely nothing to do with actual lengths of the segments. In this 4-segment spline, for example, tf of 0.5 will not match midpoint of spline length at all and will instead always sit at control point 2. Total f range is divided evenly by segment count, so every segment receives an even piece of total f range from 0 to 1. Don't worry though, if you need to work with true lengths of a spline, there are of course dedicated methods exposed just for that. For the sake of clarity, we will always refer to local fragment or segment time with f and to total fragment or spline time with tf. With that in mind, tasks like drawing a spline on a screen or moving an object along a path become conceptually simple. Just request positions for enough f values 0.1, 0.2, 0.3 and so on, and you have a path, a continuous set of points in other words. Now let's return from under the hood of a spline back to actual editor work. Spline components have lots of properties, and it's time to take a look at them all. We'll start with the general property group. The first property is called interpolation, and simply speaking, allows you to choose the type of a spline. There are 4 types available. First one is linear, and not much can be said about this one. It's pretty self-explanatory. Control points are connected with straight lines. This type is extremely performant and very simple. The next spline type available to us is called Catmull-Rom. Those splines are fast to calculate, easy to work with, and result in natural, smooth-looking curves. Unlike linear splines, they need at least 4 control points to calculate each segment. Don't worry about the border segments though. By default, Curvy calculates the 2 missing control points at the spline start and end automatically. You don't need to worry about those points, just keep in mind that there are hidden control points here and here. Next type available is called TCB or Kachenek-Bartels splines. These are similar to Catmull-Rom splines, but use 3 additional parameters you can see here. Those are called tension, continuity and bias, hence the name TCB. Playing with those parameters can give you some pretty weird looking curves. There are some presets available to match Catmull-Rom splines, simple cubic splines and linear splines, but you can input your own values, of course. For example, tension defines how far from control points the curvature is being offset, as you can see here. And finally, the last type available is perhaps the most widely known one. It's called Bezier. Bezier splines are different from cut-pull-rom and TCB ones, because curvation of a segment is dependent only on its boundary control points. So this segment is controlled only by those two control points. This segment is only controlled by those two control points, and so on. Aside from positions of those two control points, shape of a segment is controlled by so-called handles. Each control point has two handles, incoming, situated before the control point, and outgoing, situated beyond the control point. By default, Curvy controls handle positions on all control points automatically, creating smooth curves based on distance between control points and path direction. But we can disable that in the control point inspector to take a look at the handles and modify them ourselves. This is accomplished by disabling the auto handles toggle. Now we can see them. As you can see, their influence is pretty simple to understand. The distance between the control point and the handle defines, so to speak, the initial radius of a curve, while relative position between the control point and the handle defines the direction spline will take. If you have ever worked with Unity animation curves, you already know Bezier splines inside out. Let's shift our attention to the toolbar. As you might have noticed already, it's contextual and is based on your current selection. Right now, we are selecting a Bezier control point, and the options on the left reflect that. Hovering a pointer over any of those options will trigger a hint to appear. For example, one of the currently active options is Sync Direction. It tells Curvy to automatically shift the position of an opposite handle as you modify one of them, keeping them parallel and therefore keeping the curve continuous. If you want to break the curve, for example to create a trajectory of a ball jumping on the floor, you can disable that option and position both handles independently. Or you can simply turn one of the segment ends linear by setting the handle position to 0. Let's drag the outgoing handle somewhere and try another option, Sync Length. This one is fairly self-explanatory. It syncs the distances from the control point between both handles. Let's set the auto handles mode back on and try the last remaining option in the Bezier drop-down of the control point inspector, called distance percentage. By default, it's set to 0.39, but we can modify it to a heart's content, from 0 to 1. It offers you some limited control over the shape of a spline with auto handles. The value of 1 tells Curvy to generate a handle position offset from the control point by distance to the next control point. As you can see here, those two distances are equal. And the opposite value of 0 tells Curvy to place the handle right at the control point. This covers all the Bezier-specific options of the control points. We have not yet covered the general set of options in the control point inspector. They are linked to spline object configuration, and we'll get back to them in a minute. Before that, let's quickly cover the remaining control point specific options in the toolbar. Select Parent and Select Child options are self-explanatory. They can be used to quickly switch the selections as you configure both spline and control point properties. Let's select a single control point again. Previous and Next options allow you to switch the selection from a currently selected control point to respectively a previous or next control point in the spline. We have already covered sync options for handle editing a minute ago, so let's go further down in the toolbar. Next we have a Shift option, which is useful when you need to quickly reposition a control point but don't want to waste time adjusting X, Y and Z position of its transform. It allows you to shift the control point using the current spline path as a guide. For example, we can take this control point and shift it closer to the next, or backwards on the path. It's pretty useful. The first option allows you to make the selected control point the first one in the spline, as you can see here, or as you can see here, or with this control point, and so on. And finally, the split option allows you to split the spline into two splines at a selected control point. As we have said earlier, we will cover the remaining connection-related options later, as they warrant a separate video. Let's return to the Spline Inspector now. We have covered interpolation, but we have a lot more options to study. Next option after interpolation is Restrict to 2D. It will switch transform position gizmo in your scene view into 2D mode, prohibiting translation of control points on a Z-axis. This mode won't automatically set the coordinate of your points to 0, so that you won't lose any work when you accidentally click that toggle, but the inspector will warn you if your control points are not coplanar and will display a button allowing you to fix that. Splines restricted to 2D on the axis can be very useful for a number of objects, like UI elements and shape extrusion cross-sections. Next option is Closed. Enabling it will obviously close the spline, connecting the first and last control point with another segment. Next one is Auto End Tangents. It is only active for Catmull-Rom and TCB splines. Remember what I said about those splines? Requiring 4 points to define a segment, with Curvy generating 2 hidden points beyond first and last ones to spare you the inconvenience. Well, you can disable that with this toggle, making the edge points defined manually and making the splines 2 useful segments smaller. And finally, the last option in the General tab is Orientation. Orientation is very important and deserves a thorough explanation. First we'll look at a sample scene and then examine how spline orientation enables it. Let's load up the sample scene 6 and enter play mode to check it in action. Here we have a ship traveling along a path using the standard spline controller component. As you remember from the beginning of this video, spline curves are at a minimum, just sets of points returned by a function, just positions in space. But here we see something strange. The ship aligns itself to the path, keeps horizontal orientations for some segments, banks on sharp turns, executes rolls. Where are those rotations coming from? Well, as it turns out, splines can give you more than just position. At any given point, you can also get a so-called tangent, a forward vector. Spline tangent visualization is disabled by default, so let's enable it through the view menu in the toolbar. Here. See those tiny little green arrows? That's what the ship is using to orient itself. But how would it know which rotation on the tangent axis to assume? That is, how would it know where the up direction is? How would it know how to roll? That's where another property comes into play, orientation. In short, orientation refers to the up vector at any given point on the spline path. Let's enable the orientation visualization too. Its toggle is situated in the very same menu here. As you can see on the sample spline, yellow lines show the upward orientation, which the ship is closely matching as it follows the loop. And here it goes flipping back up, and here is the bank, see? And here is the roll. Let's create our own spline from scratch and walk through the options. I'll enter the Draw Spline mode after creating the spline using the context menu and place a few control points on the plane. That's enough. Next, I'll close the spline and will change the spline reference in the ship controller to our spline, so that it will travel along our new path. As you can see here, in the play mode, it works as expected. Splines have multiple orientation modes. As you can see here in the Spline Component Inspector, we have a drop-down with 3 orientation modes available. The first one is None, and is fairly self-explanatory. Orientation is not calculated at all, which makes this mode the most performant, but fit only for use cases where you need nothing but position from the spline. Usually, that can be the case for UI elements, like windows or individual sprites. Second orientation mode is called Static, In it, orientation can be different at any point of a spline path, and it is linked to rotation of control point transforms. As you can see here, rotating one control point pushes the orientation sideways, which has an immediate effect on our ship, which is pushed along a path. But having every single control point exert influence on orientation can be inconvenient. There is a third orientation mode, dynamic, which solves that. In it, orientation is not hard linked to every single control point. Instead, it is controlled by a specifically marked control point you can choose, which are called orientation anchors, and is smoothly interpolated between them using a rotation with the least possible angle. The first control point becomes the first orientation anchor. You can make a control point an anchor with a toggle in the control point inspector. Let's make the ship rotate to the side by control point 2 and return to horizontal orientation by control point 4. Both of those points will become our orientation anchors. Rotating the control point to influence the orientation is a bit inconvenient though. After all, the z-axis is not matching the spline. But there is an option that can fix that. Control point inspectors in the static and dynamic mode offer, as you can see, an option to bake orientation. What this does is snapping of a control point to the spline tangent axis, making rotations on the axis the only input needed to define any orientation. This makes any setup faster. Let's repeat this for control point 2, inconvenient rotation. Then we bake. Now we have a convenient way to adjust orientation here. This option makes any orientation setup quite a bit faster, so try to use it often. The dynamic mode gives you the greatest degree of control over spline orientation. For example, you can add new control points anywhere without disrupting the orientation, which is completely decoupled from them until you explicitly mark a control point as an anchor. That's what I'm doing right now. Note how rotations of those points have no effect on orientation, which continues smoothly from one anchor to the next. Another useful option is furling. Let's say we want our ship to do a barrel roll from control point 4 to the end of the spline. We can, of course, achieve that by chaining half a dozen of control points marked as orientation anchors. But that will take time and won't always be convenient, due to dynamic mode attempting to link orientations using the shortest rotations. So, instead of that, let's try the option specifically developed for such a case. As you remember, in dynamic mode, orientation is decoupled from segments between the control points and is instead smoothly changed from one anchor to the next. Paths which anchors divide splines into are called anchor groups. In our case, we will be looking at an anchor group spanning between control point number 4 and the end of the loop. In other words, the control point number 0. Other anchor groups contained in our splines span from control points 0 to 2 and from 2 to 4. Let's say we want the ship to make multiple barrel rolls in that area. Let's examine the swirling modes available at control point 4 and see which one fits our needs the best. First mode is called segment. With it, the number of swirls set through the field will be applied evenly across every segment until the next anchor. As we have 3 segments in front of us, as we have 2 segments in front of us, field value of, let's say, 4 gives us 8 swirls, which you can see from the visualization in the scene view. Second mode is called anchor group. With it, as you can see, the number of swirls is split by the number of segments, with each segment receiving an even fraction of a number. In our case, with a total of 3, each of the 2 segments received around 1.5 swirls, which results in a total of 3 swirls received by the end of our group. Let's shift one of the control points to illustrate a downside to those 2 modes. Moving this one closer and this one closer. Alright, As you can see, both of those modes can result in uneven rotation rates, as they are dependent on segments. In both segment and anchor group modes, segments will receive identical number of swirls, no matter their absolute length, which is not always desirable. What if we want our ship to have a constant roll rate, no matter whether a segment is 1 meter long or 50 meters long? Well, the last swirl mode, called Absolute Anchor Group, takes care of just such a use case. As you can see on the orientation visualization, this mode makes the change evenly distributed over the length of an anchor group. This just about covers the orientation. We have finally finished the overview of the general spline properties, only a few bits of information left, so hold on just a little longer. Okay, all that's left is to take a quick look at the Advanced Settings tab in the Spline Inspector. What do we have here? First of all, there are 3 visualization options. Show Gizmos is enabled by default and controls whether the curve and its control points are visible in the scene view when the spline object is not selected. This is useful when you walk in a busy scene with dozens of splines. As you can see here, it's no longer visible deselected, and if I enable the options again, it stays visible. As I've said, it's mostly useful in busy scenes with dozens of splines which you don't want to see all at once. Color and active color options are self-explanatory. As you can see, they control the color of the curve and control points in selected and deselected states. Of course, you can set it globally through the Curvy Preferences window. There you can adjust the default colors all new splines receive. Next up is cache density. Its effect is best seen when you have orientation visualization enabled. As you might already be aware, Curvy is pre-calculating some spline data for a limited set of points and caching the result, tremendously speeding up performance. This setting is relative, allowing you to tweak the number of cache points that segments will receive between none and the current maximum per world space unit. How do you set that maximum? If, for example, your scene is pretty small and default number of points per unit is not high enough, even at 100% spline cache density. Well, there is a global setting determining the maximum possible number of cache points per world unit, and it's called max cache PPU. For example, if you set it to 10 and set the spline cache density to maximum, a spline segment with a length of 20 units will receive around 200 cache points. Try not to go overboard with this global value. There is absolutely no benefit in having 1 point per centimeter in a kilometer-long spline, and the number of cache points has a direct performance impact in some tasks. Next up is Use Pooling toggle. It's enabled by default and should usually stay that way. Pooling of game objects is an optimization that has some overhead, but in absolute majority of cases it should improve performance in your spline objects. After it, you have Use Threading toggle. This one is less straightforward. It's off by default as it can add significant overhead for some splines with little performance benefit. Still, it can be useful for some complex, highly segmented splines, pushing overall performance beyond the point possible for non-threaded splines. We recommend you to carefully profile the performance with this toggle both on and off to determine whether it's useful for your particular case. Next up is Check Transform. This one is pretty simple. It checks the transforms of the control points at runtime to see if they are being shifted, and rebuilds the spline if that's the case. Outside of play mode, splines are always automatically rebuilt, but at runtime you don't always need to check the control points at each update, so consider leaving this toggle disabled for static splines you don't intend to modify during the game. And finally, there is a drop-down allowing you to define which event should be used for updating the splines. It allows you to switch between using update, late update and fixed update. This pretty much covers all the inspector options. Only one last thing is left for us to explore. There are some toolbar options we haven't yet covered. Let's get to them. They are available when a spline object is selected. First of all, set pivot, which predictably allows you to set the pivot of the spline object. That's pretty useful if you want to rotate it or otherwise rely on specific world space position of the spline. Let me disable the sky to show it more clearly. It's a bit similar to UI anchor controls. Same layout with 9 possible snapping points. Flip is self-explanatory. It just flips the order of all control points, making the last one the first one, and so on. I'll walk through the point list now to show how it is reversed. And finally, there is normalize, which will set the scale of all objects to 1. It's useful if you weren't careful with scaling, for example, using it to tweak a group of control points. Alright, that was a huge tutorial. It ended up quite a bit longer than I have anticipated. Hopefully you'll leave with quite comprehensive understanding of splines, which is pretty important for all the work you will be doing in Curvy. See you next time!